Okay, I'm just going to say some of the things again just for completion. So I mentioned that we will now look at transmission line resonators because at high frequencies, the lumped element circuits really don't exist. But the fact that we are only interested in a small range of frequencies allows us to use lumped element circuits, which look ideal in that small frequency range. But alternatively, we can also use transmission line sections to achieve the same effect. Again, only over a narrow range of frequencies, but since that's okay, it's fine. So we will look at resonators now made using sections of transmission line and see how they compare and contrast, with these simple LC models. So what you'll actually end up seeing is that this idealized LC circuit is also an effective model for many different circuits around a certain range of frequencies. And this also allows you to, when we now go into the context of quantum computing or quantum circuits, it's very easy to write down the Hamiltonian of an LC circuit, but not of that of a transmission line. It's a lot more complicated. So these effective models are useful in that sense as well. So let's look at transmission line sections. But before that, just wanted to look at the impedance of this parallel LC circuit, which we have been studying for the last couple of classes. So I'm going to go and set up the Z in measurement, which is under linear and all the way at the bottom. And this, since this is a single port device, this basically should give you the impedance of the particular circuit you are looking at. And we will look at the real and imaginary parts of this Z in. The circuit right here. So always remember to make sure the data source is selected correctly for the one you are. So schematic 1 is this. Maybe I should rename this. One second. Yeah, okay. So now let's look at this graph. Let me make sure what the frequencies are. 4.8 to 5.2. This is the fine sweep. So let's go a little broad. What happened here? I think I might have changed the x-axis earlier. All right. Okay, maybe it's too broad. Let's go to 4 to 6. Okay, so it's looking a little funny, and that's because the impedance of this thing actually goes to infinity. As you might have seen, we've discussed this before. Just make sure this thing is looking. Yeah. So the real part, of course, is 0 because this is a purely imaginary impedance. So we might as well just disable that. And the imaginary part is some small number at both large, low and high frequencies. But around the middle, it has this kind of behavior. So let's actually zoom in. So it's going to plus infinity and then sort of comes back from minus infinity. This you should have seen from your mathematical formula. So because the z has this infinity, sometimes it's useful to look at y, which is 1 over z, because that will have a slightly better behaved response. Okay, so let's expand out a little bit so that we can see this. Right, so it actually has a very sort of very simple looking behavior, almost looks like a linear curve, and it reaches 0 at the resonant frequency. Okay, so this is just 1 over z. Okay, y is called the admittance, it's just 1 over the impedance, and that's what it, so that's why when you plot the 1 over, this part goes to infinity. Okay, so now if we look at this behavior and now try to see, let's call this TL section. Now I'm going to see, just put a section of transmission line. Okay, and maybe we will leave it open on one side. Let's choose 5 gigahertz as the F naught, and let's start with 180 degrees. I'm going to put a port here, and we can now plot the same quantity for this thing and plot it in this graph. So I will change the source and only look at the imaginary part. Enable that. Let's see. Okay, so wait, I plotted the z. Okay, so the blue one is the transmission line because that's the first one here. This is the TL section you can see in the legend. This is visible. And the pink one is this. So you can see that they actually have a very similar behavior in this range of frequencies. But there is a difference, which is this slope, right? But they are both crossing 0 around some value, which is close to 5 gigahertz. In fact, the blue one is exactly at 5 gigahertz because that's where we have set this frequency, and it's 180 degrees at that length. The other one, because I think we chose a value of L and C, which is slightly different, but that is irrelevant. Okay. Now, can someone tell me what property of the transmission line I can change to make the slopes match? Jay?
I would guess the impedance.
There is only one thing we can change here, right? Because the 5 gigahertz is set because we want the thing to have a resonance around 5 gigahertz, or at least we see that it crosses. And this 180-degree length, it's also related to the effective length. So if I change this, it's going to change the location of the crossing. So the only thing we have left is actually the characteristic impedance of the transmission line, right? So in fact, just to convince ourselves, let's look at what happens when we change the other things. So if I change the electrical length, you can see that the point at which it crosses 0 is changing as expected. So that changes the frequency. If I change the F naught, the same thing happens because they are basically interchangeable, right? So the phi, so the only other option I have is this Z. So if I increase Z, it actually is becoming flatter, which means I need to decrease Z. So now let's actually make fine adjustments to the frequency of this section, the F naught, so that the two actually line up. Oops. See if you can make final adjustments to this. All right. It looks pretty good, but you can already see that if I try to match it in one side, it starts to deviate on the other side. But right in the middle, it looks really like the behavior of the parallel LC circuit. Okay. Now, one thing to note here is that this is happening at a value of Z naught close to 4.9 ohms. As I told you that it is very hard to make transmission lines in practice which are too far away from 50 ohms. So either much lower, say anything below 25 ohms, and anything about 70, 80 ohms is actually somewhat impractical. There are special cases where you can do it. And what is this number 4.9 actually related to? If we go back to the parallel LC here, and I guess we have defined them in terms of these global definitions, which are here. So can, Joydeep, can you guess whether this 4.9 ohms we have now found empirically by just matching the slopes of this behavior? By the way, I hope you guys realize that if I ensure that this new device has exactly the same frequency response as the other one, it's effectively the same thing, right? This should be clear because that this frequency response or impedance as a function of frequency is essentially the only thing that the defining characteristics of that. So Joydeep, any guesses?
Do they have the same characteristics impedance like the ZR square root of L by C?
Let's see. We can use the equation here to calculate that. So I will define Z of parallel LC equal to square root of LRG over CRG. But here we have to be careful because the units are not the same. I mean, first of all, they're not the same, but one is in nanohenry and the other is in picofarads.
Picofarad, yeah. So,
right? So basically 10 minus 9 divided by 10 minus 12, it means multiplied by 1,000. So I can just multiply by 1,000 here. Okay, put that. And here's another trick.
G is
sorry. And there's another trick in microwave office. If you want to display a value you have just calculated like this, you just type that variable and put a colon next to it. Okay, so now if I run this, and this is the value, okay, 3.162, and that looks pretty close to the value we just computed. In fact, let's put 3.162 here and see how this graph looks like. Oh, that's interesting. It's not exactly the same. I would have expected this to be the same. What happened? Okay. I'm not sure. Maybe I'm misremembering the exact formula for this. So maybe there's some additional factor which comes in when we talk about this thing. But essentially, it is related to the impedance, the characteristic impedance for the parallel LC resonator. It might not be exactly the same. There might be a factor of some pi or pi by 2. I will check that. It's actually there in POSAR. We can check it. And now the question is, why is that actually the case? How is the parallel LC's ratio of these L's and C's which we have made here? Why is that connected with the characteristic impedance of this section of line? Anybody? Srijita?
Why is it connected to the characteristic impedance?
Yeah. Like why is the characteristic impedance of this transmission line affecting this slope, which we have connected to the characteristic impedance of the parallel LC circuit? Like what's the connection here? So remember, we are basically trying to mimic the behavior of a parallel LC circuit with the help of this
using the transmission line.
Yes.
Yeah.
Right. Joydeep?
So I think I can imagine this transmission line is as introduced in the first class, that it is made up of L and C. So in that case,
yeah, that's sort of basically the right answer. Remember the modeling of the transmission line which we looked at in the earlier classes, and you hopefully have seen this telegrapher's equation. The transmission line can basically be modeled as LCs, 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 like a network of them, right? So obviously, if it is behaving like some inductor and capacitor, it has to be connected to that. And the capacitance to ground, right? So it's something like you have these network. So this L and this C is what determines the Z naught, right? So a large capacitance would mean a smaller impedance, and here we have basically a a fairly largish capacitor which we are using with the CAG is about 10 picofarads. So the effective inductance and capacitance which are going to come out of a piece of transmission line is related to the underlying model, which is this LC thing. So it's not surprising that they are related. It's not exactly the same that you get. So what is not matching is the value of Z0, which gives me the same slope as that of the parallel LC we have used. Is the two numbers are not matching because it's not exactly equivalent to a value of L and a value of C, a single L, a single C, right? So you can basically also say that, okay, what is, if I want to make an effective capacitance out of this piece of transmission line, you might say, okay, it has a capacitance per unit length of something. You know, remember these L's and C's are capacitances per unit length, right? So actually, I should really put delta X here to both of them, right? So then you can somehow say that the effective capacitance is that capacitance per unit length multiplied by the length of this transmission line. And that's an approximation. It's not exactly the same thing. So that's why these two things are related to each other. The point essentially I'm trying to make here is, in order to control the characteristic impedance of the resonator you're trying to make now, remember that in a parallel LC, L and C or resonant frequency and characteristic impedance are equivalent ways of parameterizing that oscillator. So those are the only two properties you have. There are only 2 degrees of freedom, right? 2 variables, L and C. So sorry, not degrees of freedom, 2 variables which control the properties of that resonator. And that is the L and the C, or omega naught and Z naught. So here, the same things apply. The frequency is basically controlled by this parameter here, which is related to essentially what is a lambda by 2 section. In this case, remember I've chosen 180 degrees. We will come to why 180 degrees. And the frequency is, you know, basically the frequency at which this is 180 degrees. Then the only other parameter you have under control is Z, which controls this distribution between inductance and capacitances in the transmission line. Okay, so that's essentially basically tells you that one can make a resonator out of this because its frequency dependence seems to match exactly the one we are
So in the transmission line case, you have not grounded the transmission line, whereas in the LC case, they're in parallel and they're both grounded. Does that matter? I mean,
so that's a good question. It's a little subtle, so but let's discuss that. See, you have to remember that a transmission by definition always has a ground. Okay, when I draw, and especially in microwave office, you have to be careful about this because you don't often see the ground explicitly present here. But really, this circuit here is remember the port always has a ground reference.
yes.
And when you connect it like this, the ground of the transmission lines, which is basically the outside body, is also assumed to be connected to ground. This is not made explicitly in the way it displays here in microwave office, but that's what it means here. It's not, you cannot have the circuit complete if there is no ground connection. You can't just have a single terminal going in and going out. All the grounds things are happening because the transmission line is also, you know, it's this. So there are these capacitances which are connecting to this ground plane. Okay, so this is grounded, and hence consequently, there is a ground conductor on that.
Yeah, but I mean, I was
Okay.
asking about that last terminal. I mean, whatever is connected to
So, but
that.
that is, so that I'm coming to that, but that is a different point in terms of what it means to connect to the ground. The last terminal, if I connect this to ground, it's not the same as not having a ground or having a ground. This is basically now the boundary condition, because remember that this part here is also two terminals here. There is a ground and then there is the center pin. This part is effectively grounded. It's this part which I have left undisturbed.
Yes. Yeah.
Okay. So this is now a boundary condition I have specified for this section of transmission line. I've chosen it to be an open. So this boundary condition is basically an open circuit, because there is no current flowing between that terminal and the ground at that particular boundary. I could have, the other possibilities are that I could have shorted this. So this is also ground. And then I could have connected this to the ground, the center pin also. That would be a short circuit, which means that there is a 0 voltage difference between the center pin and the ground at that location. Okay. Again, remember that this is a finite length. Shorting it here doesn't mean it is shorted everywhere. Okay, that's how we think in low frequency DC circuits. But here, that short circuit or open circuit specifically only applies to that particular boundary, that point. Okay. Now, how does that connect to this being connected to ground here is a completely different argument, because, for example, I could consider this this transmission line. I could just make, I'm saying that, okay, this is a very small piece of transmission line. So let me make just 2 capacitors and 1 inductor in between. And this is what I'm deciding to model my transmission line as. So this part is grounded, this part is grounded, and this part is connected to your port. Oops. Okay. Now, this now looks a lot similar, even though I have done nothing to this part. This is starting to look similar to the parallel LC circuit, which has an inductor to the ground and a capacitor to the ground as well. Okay. So that aspect has no connection here of how I've connected the parallel LC circuit. So this ground and these grounds are 2 separate things. And the fact that this is left open is 2 separate things. Okay. So this I have drawn only as an example. In fact, this can be completely wrong depending on how much length you have. So this idea, I just also explained that, I should imagine this as a network of L's and C's. It's a little bit more subtle than that, because the finite length and the fact that the signals can propagate back and forth and give rise to interference can make this thing look like something completely different at a different frequency, even though the section of the transmission lines looks exactly the same. Okay, so we will actually look at that next to see this. So, I mean, I know I have not given a very convincing answer here, but I hope you understand the difference between grounding this point versus having a ground here. Jay?
Yeah.
Okay, they are not the same thing. What is important is this, that from the point of view of the port, they both have exactly the same admittance as a function of frequency in a range of frequencies we are interested in. Okay. And that means that effectively they are identical devices, their performances or whatever their responses will be identical at these range of frequencies, because there is nothing else to define. That's the only thing there is. Okay. Now, we will look at this response at a much wider range of frequencies. Okay, so we have sort of matched it at around this 5 gigahertz frequencies. Let's go and increase the range. Let's go all the way from 1 to 20. Let's cut down on the points a little bit. Now let's see how it looks like. Okay, so let me do something here. Oh, this is not going to help. Oh, sorry. Yeah. Okay, so now it will be clear. So remember, we were here before at around 5 gigahertz. The blue curve is the transmission line, and the pink curve is the parallel LC circuit. Okay, so this is where it was matching. And now you can see how the parallel LC circuit behaves over a wide range of frequencies versus this section of transmission line over the same range of frequencies. And it's completely wildly different, right? The admittance goes to infinity at some point. So all of these points here where it is sort of going very high, it's basically the same behavior we saw for Z in over here. Now the admittance is showing the same behavior, but at a different frequency. And this frequency is around 7.5 gigahertz. And then if you look here, this again is crossing 0. And it looks very similar to this behavior, right? It's crossing 0 here. It sort of has a linearish slope around there. This is the same thing. This also looks exactly. So this is what I was trying to say, that this simplistic model I just drew, 2 minutes ago, is only an approximation. And I was just trying to make that point about which ground is relevant and which ground is not relevant. It's not, you can't really look at the physical structure and say, okay, this is the equivalent circuit. It really now depends on the frequency response. And then from there, you have to infer what the correct model is, okay? Now, what does this tell you? Let's look at the simpler thing first. So out here, we've already seen this looks like a parallel LC circuit. This here probably, has the same behavior. The only difference is this is now crossing at roughly 10 gigahertz or so. So it must be another parallel LC circuit, just with a different frequency. And same thing out here, okay? So one way of thinking about this is that, oh, this circuit is actually several different parallel resonators, all of them at different frequencies, and they go as like 5, 10, 15. So they are the harmonics, right? Now, this is not surprising if we think about the transmission line as a transmission line section, and you say, oh, okay, this is just now so one amount of wavelength fitting in this thing versus 2 wavelengths fitting in this 3 wavelength fitting. So remember that this section, as defined by here, is a certain physical length which corresponds to an electrical length of 180 degrees at around 5 gigahertz, which means at 10 gigahertz, this would correspond to a situation where the wavelength is half, the physical length is the same. So that would mean it's 360 degrees at 10 gigahertz. This section of line is 360 degrees at 10 gigahertz. Okay, so we can just quickly check this. I mean, this is trivial, but let's just check that. I'm going to freeze this. I'm going to go back here. I'm going to double this, and I'm going to double this as well. Come back here. And of course, the curve is unchanged, right? Because I just compensated, I reduced the wavelength by half, increased the electrical length by a factor of 2. So effectively, it's the same thing going on. So let's go back. But what you now have that at this 10 gigahertz frequencies, you now have a full wavelength. And now, so full wavelength is fitting inside this section. Similarly, here at 15 gigahertz, it's 3 lambda by 2, and so on and so forth. Right? So each time you fit some integer multiple of lambda by 2, you will get exactly the same behavior repeating. Okay. Now, what about in between here? Right? I was looking at the admittance, and so we are looking at the admittance because we saw that at this frequency here, the admittance, the impedance was showing infinity. So we said, you know, it's not easy to compare match two curves at infinity. So let's look at 1 over that. But now the admittance is showing infinities at this particular point. And where is this point? This is exactly halfway between this and this. Okay, 5 and 10, and this is roughly at 7.5 out here. All right. So let's see, okay, now we have infinities here. So maybe we go back to impedance for the transmission line section. So let's look at the impedance here. And now you see that at this particular point, your, which was initially, in fact, let's go back, I'll freeze the trace. Why didn't it freeze? Oh, maybe it's because I'm changing the measurement here. Okay, let's just use this other one for the time being. Comparison. All right, there you go. Okay, so the admittance is the pink one, which is what we were looking at earlier. That was crossing 0 at the resonant frequency of that parallel effective circuit, which is exactly where the Z was infinite, and it's now going from plus infinity to minus infinity. And now you see that here, where the admittance is going through infinity, the impedance is going through 0, and it again has this really nice sort of linear kind of behavior out here. Okay, just to show you this more clearly, let's zoom in around this frequency 7 to 8. Okay, so here's this is now the impedance, but now at 7.5 gigahertz, and it's showing this nice linear kind of behavior. Any guesses? What is the equivalent circuit for this frequency, which would give you the same behavior? So remember, this is the transmission line section we are looking at. And earlier we were comparing the transmission line section to a lumped element model of parallel LC circuit at 5 gigahertz. This one is having a pole in the admittance at 7.5 and a 0 in the impedance. What circuit would show this behavior? Lumped circuit. Jay?
So admittance is just a reciprocal of.
Yes, admittance and impedance are just reciprocal of each other. But here the blue curve is impedance, not admittance.
So here probably you can think of it as a series LC.
Exactly. Because a series LC actually has zero impedance on resonance. We already discussed that. So this here at 7.5 gigahertz, a section of transmission line which is 180 degrees at 5 gigahertz is behaving like a series LC circuit at this frequency. Okay, if we let's convince ourselves of that. Let's go here, let's duplicate this, rename this. Oops. I'm going to change that. Okay, I'm just not bothering to turn it around, but that's your series LC circuit. Let's go back here, change this one to series LC and ZN. Imaginary. Because the values of that thing might not match exactly. Wait a second, what did I do? Oh yeah, sure. Just looking. Oh, of course, yeah. It didn't work because I did not change the frequency of the LC. So remember, the LC, parallel LC and series LC have the same resonant frequency, which was designed to be at 5, but we were looking at the 7 gigahertz operating point here. But you can now see that at 5 gigahertz, the series LC has a linear slope just like that. So, okay, this is good. I can now show you another thing. Let's go closer to that frequency, 426. There it is. And now I'm going to adjust the transmission line section to match the frequency here. So I could change the frequency because I'm operating at the frequency is higher right now. It's showing this zero crossing at a higher frequency, so I need to bring it lower. So let me lower this frequency. Okay, and then this thing is coming. And okay, the slopes are not matched, but basically you get the idea. I can make the slopes match. So really low impedance value here, 1.2 ohms or something. Okay, but it is now showing me an odd frequency, right? Some 3.36 gigahertz. That doesn't seem to match with this 5 gigahertz number here. And the reason for that is that this 180 degree length is not really the correct length to think about in this case. So I'm going to make this 90 and then adjust this frequency here. Now you see it matches at 5 gigahertz. Okay. So this proves the point that the same section of transmission line at a certain frequency can behave like a parallel LC circuit, and at a different frequency can behave like a series LC circuit. So this again emphasizes that point about the grounding and things like that. I have still not made any connected anything to ground or anything here, right? This is still, this point is still open. Okay. But here, when you talk about series versus parallel models, it actually is related to how the waves are fitting in this section here. So that's why there are two types of resonators which we often talk about: lambda by 2 resonators or lambda by 4 resonators, like this 90-degree thing shown here. And together with that and the boundary condition determines whether it looks like a series LC circuit or a parallel LC circuit. Okay, these are the only two simple possibilities. So you either have a zero crossing in the impedance or an infinity in impedance, and vice versa for the admittance case. If you have a infinity in impedance, it's a parallel LC circuit. And if you have an infinity in the admittance, then it's a series LC circuit. Whether it is a lambda by 2 or a lambda by 4, that depends both on the length, the frequency, and the boundary condition. Okay. Now, we have so far only seen the case where this part was always left open. All right. So let me go back here, simulate over a larger frequency range so that we can see this a lot more clearly. Okay, so it crosses, what are we plotting here? We're plotting Z in. And let me get rid of the series LC. I think we're only looking at the transmission line now. We're looking at Z in, so which means zero crossing means series LC. And now here there's an infinity. So this will look like a parallel LC, and then this will look like a series LC as well at this particular point. Let me freeze this. Now I'm going to go here and change the boundary condition at this point to a short circuit, right? And let's see what happens to this guy. The zeros have become infinities and the infinities have become zeros. You see that? This was zero crossing. Now it has this vertical transition, which basically means it's going to infinity and coming back. And this was that vertical transition. It has now become this simple zero crossing here, and so on and so forth. So that's why I said that the boundary condition also plays a role on determining whether something is going to look like a series LC or a parallel LC for a given length of a transmission line, right? Now, all of this is nothing but just this interference of waves going back and forth, and then at the boundary condition experiencing, you know, an open circuit or a short circuit. And you probably know this maybe from a different context, but the way the wave reflects at a boundary condition depends on the type of boundary condition you have. And remember that the expression for gamma is Z load minus Z naught over Z load plus Z naught. And remember, this gamma in general is a complex number with a sign as well. So every time ZL is less than Z naught, gamma is less than 0, right? And ZL greater than Z naught, gamma is greater than 0, which means for a short circuit, ZL is 0 and gamma is -1. So gamma for ZL equal to 0 is -1, and gamma for ZL equal to infinity is +1. Okay. This means if it is 1, it means no change in amplitude. And the sign tells you whether there is a phase flip or not. Right? I mean, maybe you have seen this in the context of optics as well, that there is a sign change in reflection. Even in quantum mechanical equations, this happens. It's all just wave phenomena. So that is the reason why the interference condition changes. Because if the wave is now coming back with a negative sign, then whether it will constructively or destructively interfere with the incident wave at a particular length will change, because it is completely opposite. So now you can see that why going from an open circuit to a short circuit completely changes what we used to have as what looks like a parallel LC behavior to a series LC behavior. Okay, so I hope this thing is clear. You can work this out all nicely mathematically, and there is a nice description of this in POSAR, where you can, there is a general expression for writing down the, if you have a section of transmission line, the expression for Z in for a certain length and a certain boundary condition. So if in general, this is some Z load, you can write down a general expression for Z in. In fact, you must have seen this in the context of the impedance transformer also, because that is exactly the same thing, that how this impedance here, it's transforming to an impedance here. So you can also see that a short circuit can get transformed to an open circuit. And that means a short circuit means Z is 0, right? And now it's gone to an open circuit, Z is infinity. And then that looks like a parallel resonator behavior in terms of its frequency dependence around that particular frequency. Okay, so you can see all of these limits in that formula, which is basically has some trigonometric functions in there, and depending on the exact boundary condition and the length, the interference condition changes, and that gives rise to this different behavior. Okay, so to now think about these resonances in a little bit more conventional fashion in terms of how the waves get fit and all. So we can just look at this. So some basic ideas to keep in mind. First thing to remember is what are the boundary conditions. So again, to compare, remember we have this business of Fabry-Perot resonators, which usually have partially transmitting mirrors or fully reflecting mirrors. So let's say that this is the partially transmitting mirror. Light enters, reflects partially, transmits partially. Here it fully reflects and then comes here, and then again partially transmits and partially reflects, and then you have multiple waves. This is exactly equivalent to the situation here, okay, in this particular case. Why? This boundary here is like the perfectly reflecting mirror like this one. Because any wave which enters here, there's nothing for it to do, it can only go back. And in this case, because it's a short circuit, it is going to go back with a sign inversion. That of course is not obvious, there's no comparison here, but it depends on the nature of the reflecting surface here. Because I could have had an open circuit here, and that would have also done the same thing. It's a perfectly reflecting surface, but without a phase change, okay? Here, this is the other boundary between the port and the transmission line. Why is there a mismatch here? Because remember, you need two boundaries in order to confine the wave to create a resonator. Supriyo, what is the reason for mismatch at this boundary?
This characteristic impedances are different.
Exactly.
For the, yeah.
So this is, remember, we were trying to match it. We got something like 4 ohms. So this is a 4 ohm transmission line, and it is now encountering a 50 ohm load here. Okay. So that is a mismatch. And that causes the wave to reflect at this boundary as well. It is not as strong a mismatch as this one. And again, the sign will matter because here this is a small number and this is large number. So it will have a reflection with a positive reflection coefficient, all right? So it's these two different kinds of mirrors which are effectively setting up this resonance. This is what is causing the reflection on both the ends. The way to think about or visualize how the wave, the standing wave, fits inside here is simple. Every time you have a short, this means that at this point, the voltage at, let's call this as x equal to 0. So voltage at x equal to 0 is going to be 0 because it's a short circuit. So if I now try to draw the standing wave as voltage as a function of x, and let's call this as x equal to minus L, then this voltage is going to start at 0 and it's going to have some maximum value at this other point. Okay. Now, if one sort of looks at this as a part of a sinusoidal oscillation, then this basically is like going from here to here. Right? And this is basically 90 degrees. That is this 90 degree, which is lambda by 4. And this also looks like this. Remember, this is full lambda. So this is lambda by 4. Okay, so this is called a quarter wavelength resonator, because at the resonant frequency, which in this case is 5.04 gigahertz, a quarter wavelength will fit between the two boundaries of this thing. Okay, and it's quarter because of the two different types of boundary conditions which are here. One is a short circuit, the other one is a open circuit. You know, it's not perfectly open, but it is more open than this one. And that is when you have the possibility of having a node at one end and an antinode at the other end. Okay. Now, so just to confirm this, because all of these things are important to figure out what the correct frequency. So this is lambda by 4 or 90 degree at 5.04 gigahertz. And this is now, one can't shift without the thing still being there. And you have here at 5.04 and infinity in the zine, which means it is a parallel LC circuit at that particular point. Right. So this tells you what the type of resonances, resonator effective model you're going to get. Now, if this was an open circuit, then you would have had a lambda by 2 resonator at 5 gigahertz, sorry, lambda by 4 resonator at 5 gigahertz, but with a 0 crossing at 5 gigahertz, and it would have been a series LC oscillator. But it is still quarter wavelength. But now you have to imagine that the voltage function looks like this. Okay, because here you have an open circuit, which means the voltage difference can be maximum. And on this side, you know, you have some connection to an impedance. So it's not exactly 0 here, but the wave will go this way. Alternatively, so this is V. You could also now think of I instead if you want. And the open boundary condition means that the current here between this and ground is 0. So you could draw the same waveform, standing waveform like you did last time for the short circuit, but now change voltage to current. And now this looks like this. Okay. Now, usually for using transmission line resonators, this simple structure where you have an open or short on one end and just a direct connection on the other end will never work in practice. And the reason is basically this value here. You had to adjust the impedance to some unrealistic value for it to actually create a resonator. And the reason is exactly what I had asked earlier. This mismatch is not nearly strong enough to confine the wave, especially if Z is close to 50 ohms. And I said that in practical situations, it is difficult to make transmission lines much different from 50 ohms. So you might be able to make 25 ohms. And in that case, this will not be a sufficiently big mismatch to confine. This directly relates to the quality factor. So remember last time we were trying to do this for the series LC resonator, and it was giving very, very low Q because of the way the typical values of the L's and the C's were. It's exactly the same thing. So in a more practical situation, you're always going to have to add some other kind of reflector here. And we already discussed one kind of reflector, which is a capacitor. So a small capacitor here will allow you to make a much bigger mismatch. So again, it's a small capacitor, so not much current can flow through the capacitor, but a large voltage difference can drop across it. So then that becomes an open end. So let's now look at that. Elements, determinant. Okay, you need to put some smallish value, let's say 0.1. And then I have this. Now we have to be a little careful about how we define this so that this makes sense from the parameters entered. So remember that it doesn't matter how we define the length. There will be some frequency at which it will resonate, but whether we'll be able to predict that frequency simply by looking at these numbers is really what we are discussing here. And now let's put this Z back to something like 50 ohms because that is the typical transmission line impedance we'll be able to make. Now I have told you that this is an open end, which means I is 0, V is maximum. And this, because of a small capacitor, is also now an open end, which again means I equals to 0 and V equal to maximum. So if I start drawing my sort of standing waveform here, if I choose I, then it has to start at 0 and it has to end at 0, right? There's no other way I can draw this. And this now is 180 degrees or lambda by 2. So in order for this sort of resonator to make sense to us, and let's say I want it to resonate at 5.04 gigahertz, I need to set the electrical length to 180 degrees. If I had kept it to 90, it would have become 180 degrees at twice this frequency. So it would have resonated at that frequency. But so that we can connect this idea of when we define something as a lambda by 2 resonator or lambda by 4 resonator. If it's lambda by 2, we would like it to say 180 here. If it is lambda by 4, we would like to say 90 here, so that the frequency can be read off directly from this here. Okay, I hope this is clear. This is just, I'm trying to give you the standard nomenclature so that you can talk about these things and understand what is going on. It's just the length of a transmission line. It will have a resonance somewhere, as long as you have put 2 mirrors like you have done here. Okay, so let's go here. Let me clear this. And I'm still looking at Z in 1. And what is this? Ah, sorry, here. Yeah. And something is happening around these frequencies. Let's zoom in. 4. Something slightly strange is happening here. Let us zoom out a little bit and see what's going on. Okay, so this looks more like what we were maybe expecting. This is like now Z in, 0 crossing here, but there seems to be an infinity as well close to this particular point. Okay. Right, so let's keep this in mind. There are 2 frequencies which seems to be showing some resonant behavior. There is 4.8 gigahertz where there's a 0 crossing. And then there is this 5.04, which is very close to the length we have defined here before. Okay. Now, since when we are looking at resonators, we are mostly going to be looking at reflection coefficient. So I had moved to this impedance just to show you the matching between. I could have actually done the matching in reflection coefficient as well, but because we understand the impedance of a series LC and a parallel LC a lot more simply than a reflection coefficient, I moved to that. So let me now plot the reflection coefficient of the same quantity. Let's go to port parameters, S11 TL section, and let's say we look at the angle, and I will put it on a different axis so that we don't mix up. Okay, so this looks exactly like how we had when we were looking at this circuit. So remember, we had with just a parallel, it was just a curve from positive 180 to negative 180. When we put this thing, there was a inversion, and this looks exactly like that. But I don't see any resonance here. Okay, this looks like that this thing is going to infinity and coming back down here. So this actually is the correct resonance frequency. It is shifted below the definition of 5 gigahertz we have made here. And this is for exactly the same reason why this also shifted, and you have done this in your homework. It's because of the loading of this extra capacitor on the effective parallel LC circuit we actually have in this case. Okay, so it's a little bit confusing. Let us just confirm this again. I'm going to short this. I'm going to just kill the reflection coefficient for 1 second. I'm going to look at the Z in. In fact, I'm going to look at the Y in. Oh, yeah, sorry. Range is okay. So Y in shows a zero crossing at 5 gigahertz, which means it's a parallel LC circuit at this resonator frequency, at the zero crossing. Okay, just pay attention and go through the sequence of things I'm saying. I've gone back to creating a lambda by 2 section at 5 gigahertz. I'm looking at the input admittance because I was expecting it to have a zero crossing here, but you can see it was an infinity as well. So remember, 0 in impedance, in admittance means you are having a parallel LC circuit at that frequency, at the zero crossing. And then I put the capacitor in and I enable the reflection coefficient as well. And now this resonance here looks like the yeah, so the brown one is the reflection coefficient. So we identify this as the resonance. And at that frequency, you actually now have a 0 in the admittance. But there was another thing we saw earlier, right? Sorry, just hold on 1 second. I'm losing my chain of thought here. Yes. Here we had this as Z in. Okay. Yeah. Okay. So this is what we saw. So this zero crossing is now sort of coming from the other way. This looks like that it went to some high value and came back, but there was another zero crossing here in the admittance, which is what we are sort of used to look at. And this happens at even we were used to seeing things like this. Now this inversion is happening because of the same reason we saw with this capacitor actually introduce an additional sign inversion. Okay, so the thing I wanted to put across is that even though the admittance now seems to be showing like a behavior where it's going to infinity and coming back. The exact resonance is actually here and not here, which is evident from the reflection coefficient, that there is no resonance of this type, which you'd expect from a parallel LC circuit. So this additional capacitor is causing this thing. The loading effect is clear. Instead of 5 gigahertz, it's happening at 4.8. We can check this. We can tune this capacitor here. And if I go to a smaller value, the frequency moves to higher frequencies, just like we saw last time. Okay. So the addition of this coupling capacitor is making this connection between the series and the parallel LC is a little confusing. But by shorting this out, I was able to show you that the behavior of this part of the circuit, which is just the lambda by 2 section. So this is lambda by 2 at 5.04 gigahertz is equivalent to a parallel LC circuit. Then this whole thing becomes a capacitor in series connected to a parallel LC circuit like this. Okay, so this is how one needs to think about it. When you add this extra capacitor, it introduces additional complication, because this very tiny capacitor also acts like an impedance inverter. So it basically changes a 0 into a pole, like a Z into a Y, which is what is going on when you look at this thing. But actually, the effective model you have to really consider without keeping this coupling capacitor, and then understanding that it's a parallel LC circuit with the coupling capacitor, which gives rise to the total effect. Okay, slightly confusing. When you play around with it in Microwave Office and look at the equations, you sort of get what I'm trying to say. And the reason you have to separate this is that the resonator is really being formed by this, this section of transmission line here. This is part of the boundary condition setting situation. So you need to throw this out, and that way, I mean, not throw it out, but keep it separate, because then you can compare it with this scenario and what happens when you put a coupling capacitor here. So when you're trying to design the resonator, its frequency and its characteristic impedance, you have to really look at just this part. The capacitor is now in addition to it. So you look at the behavior of this. So now you know that a lambda by 2 section of a transmission line, which is open at both ends, because this is an open end and that is also an open end, behaves like a parallel LC circuit, which is again one of the most common things you would have. The same situation can also be obtained by, I'm going to clear this. We already seen a version of this, but now with the coupling capacitor, I will ground this. Now this is a short circuit and this is an open circuit. So now when you have short and open, it has to be a lambda by 2 resonator. Lambda by 4 resonator. So then I have to put 90 degrees here in order for it to resonate at 5.04 gigahertz. Okay, let's go back here. Look at this resonance. The loading effect is different because the effective model of this resonator is going to be different. So I'm going to have to adjust the capacitor a little bit and pull the frequency back up again. What is this? What did I change? Sorry. Not this. 50 ohms. Where's the coupling capacitor? Oh no, it's this one. 0.04 coupling capacity. Okay. Now see that this response looks exactly the same as what we just saw for the lambda by 2 section, which was open at one end, at both ends, and a lambda by 4 section, which is open at one end. The same behavior for the resonance, the same behavior for the imaginary part, which actually now seems to have an infinity here and then a 0 here at the bare, cavity section frequency. So this means that this also is a parallel LC circuit connected to a coupling capacitor. Now, let me ask you, in fact, I've already given a hint. So let's see, Srijita, is so I'm just drawing here. So this is a lambda by 2 resonator at some frequency F0. And I just said that this is equivalent to a parallel LC at F0. We also saw that, sorry, lambda by 4, I'm just mixing up my numbers. This is lambda by 4 because it's a short and an open. Then you have open on both sides. This is lambda by 2 at F0 is also an LC, parallel LC circuit. Is there any difference between the effective model of LCs for these two cases? Or are they identical?
If the behavior is same, then they should be identical.
Well, but is the behavior same? I just did something a couple of minutes ago, which should have given a hint. So let's look at this one more time. I'm going to go back to the, so in fact, let me freeze this trace here. I go back here. I remove the short circuit. Oops, what's going on? I make it 180 degrees. I come back here. I run it. The shape is the same.
Okay, so one is with the coupling capacitor, another one is without the coupling capacitor.
No, they are both with coupling capacitor. The coupling capacitor is exactly here. It's the same value.
That we are making.
Huh?
I meant the model we are making. One will be only the parallel LC, another one parallel LC with that capacitor with it.
No,
Because it's shifting the frequency.
you are in the right direction, but your explanation is not correct. Remember, the coupling capacitor is still connected here, right? It's still there. I just showed you what happened. So this out here was the response of the lambda by 4 resonator. And here is the response of the lambda by 2 resonator at the same frequency with the same coupling capacitor. So, and I said that we have to treat this part separately to consider the effective model, right? So when I'm drawing this, I'm drawing this part. So there is always going to be the same coupling capacitor. What we are observing is that the same coupling capacitor is giving rise to 2 different resonant frequencies for the lambda by 2 and the lambda by 4 section. So the lambda by 2 section has a higher frequency. So remember, this is lambda by 2. and its frequency, resonant frequency is around here at around 4.9. And for the lambda by 4, it was 4.78. So what must be going on? So remember that the circuit up to this part is the same. We also know that both of them are parallel LC circuits. Joydeep?
So when it is grounded, so for the lambda by 4 case, so I think there is another capacitor. So LC, then there will be another capacitor in series.
Capacitor where?
After this LC circuit.
Why? I mean, a short circuit is not going to introduce a capacitor. Jay?
Not sure actually.
So Priya?
So one thing is, you are asking that, so for the similar, in one case it is grounded, in another case it is open. In that case, what is the change, right?
Not just that. The case where it is grounded, I entered 90 degrees here.
Okay.
And the case where it is open, I've entered 180 degrees. I already explained why that is the case, because we're trying to fit a section of the wave with the appropriate boundary conditions. So when you have a short circuit and an open circuit, then the smallest wavelength you can fit is lambda by 4. But when you have open circuit on both cases, then the smallest you can fit is a lambda by 2, because both sides have to be current nodes or voltage antinodes. So that is the only way you can fit it. So and aside, a slight digression point here is that a lambda by 4 section, if you use, you can make the same resonant frequency with half the length of the transmission line, right? Because remember, in both cases, the F0 was 5.04, but in order to create a resonance at 5.0 or close to 5.04, I had to use twice the length for a lambda by 2, but for a lambda by 4, I had to use 90 degrees, so which is half the length. So smaller length, still the same frequency because of the way the boundary conditions are set up. So I'm asking basically, what is the difference between these two resonators? They are both, one is lambda by 4, one is lambda by 2. They both have a resonant frequency near 5 gigahertz. And they both look like they are parallel LC circuits with a coupling capacitor in this model. So what is the difference? Is there any difference at all? Or are they exactly the same? I just want to create this effective model. I know this is the same. This is also the same because I have not changed it. So how is this parallel LC circuit going to be different for a lambda by 2 versus a lambda by 4?
Okay.
And the hint is already here in what we observed out here. This is the resonant frequency of the lambda by 2 resonator, and that is the resonant frequency of the lambda by 4 resonator. Okay, look, there is a dumb answer here. I mean, the frequencies are the frequencies are different, so which means L's and C's are different. But what is actually different? No?
L should be different because in one case for lambda by 4.
Well, both L and C's are going to be different, but in what way? So the important point here is that they are both have this 5.04 gigahertz number associated with them, and just that one is 180 and one is 90. Let's look at the behavior of the admittance again. Okay. So this is now, I'm removing the coupling capacitor. So this is now, we can just model just the transmission line section. Okay. Let me clear this. Sure, maybe I'll keep it there. It is a zero crossing in the admittance, which means it's a parallel LC circuit, right? This is lambda by 2 at 5.04 gigahertz. Go back here. Let me clear all of this, add this to the freeze. Now I go back here. I add a short circuit and I change this to 90. Happen. Last chance. Is it going to cross 0 at the same point or not? Let's hear, take a vote. Joydeep, yes or no? Hello. Joydeep?
Yes.
Am I going to get a similar behavior for Y in crossing 0 at exactly the same point?
No.
Okay, he says no, it won't cross 0 at the same point. Let's see, Srijita?
No, like from the last plot, I think it should be no.
The last plus, it should be no. Okay, Jay?
Something was different, so that should stand irrespective of the coupling capacitor. There'll be some change in frequency. Is it that the
You're saying it will not cross 0 at the frequency?
No, it shouldn't.
Okay, and what about Supriya?
Not very sure, but seems like it can. Some compensating element probably is coming in the equivalent circuit. Not quite sure. Think.
Okay, let me add one more hint and I will ask all of you again. So right now we have 3 no's for 0 crossing at the same frequency and 1 sort of uncertain, but pick one, Supriyo, yes or no? 0 crossing frequency, is it going to be the same or different?
Same.
It's going to be the same. Okay, so we have 3 no's and 1 yes. Or sorry, 3 different and 1 same. Now, let me ask another question. We are talking about some effective LC circuit. Is the 0 crossing the only property which defines it? What is the second? Okay, now let me ask again. Joydeep, is the 0 crossing going to be the same?
Can the 0 crossing happen at different position of the frequency? No.
That's what I'm asking you.
Can happen, like at different multiple of the same frequencies.
Oh, it's not going to happen at a different multiple here. I mean, we are talking about,
Right.
remember, we have already established that there is a resonance around 5 gigahertz because of the way we have chosen the length and the boundary conditions.
Yes.
All I'm asking is that, is it going to be exactly at this point or is it going to be somewhere here or somewhere here to the right? Because of what we observed a little while ago when we looked at the actual full resonance circuit with the coupling capacitor.
Will be different for sure.
It will be different for sure. Okay. Srijita, use the information I have provided just now about what else can be different.
Different, I think.
It's going to be different. Now I'm worried that my own thought process might end up something completely wrong, and I wouldn't know be able to answer your question. All right, Jay, do you want to change your answer, or are you going to stick to your answer?
I'll change it just because of the fact that we're having a second round of.
Well, you never know. I could be devious.
You sound passionate enough about us changing our answer.
You have cracked my code. All right. I think there's no point in asking the question. My answer is zero crossing is same point, but the slope is different. And I was right. You see, this zero crossing is entirely, the frequency is entirely set by this number. Why? Because we match the boundary conditions to be like that. So for 180 degrees, we ensured it was an open circuit on both sides. And for 90 degrees, we ensured that was short here. And we know that this will be where the resonant frequency will be. Both of them show, we've already seen this before, both of them showed this kind of a behavior. That's, we started there, which means they both have an equivalent circuit of a parallel LC. And in fact, this goes to prove that, earlier we were when we first looked at this comparison, we thought that maybe the Z naught of the transmission line will be the same as the Z naught of the equivalent circuit we had seen earlier, which makes the slope match. And we found that it was not the case. And here is another example where it is not the case. For two different kinds of resonators, having exactly the same resonant frequency, having exactly the same type, which means a parallel LC resonance, but the slope is different. And now this should be obvious because, again, even though I sort of keep going back and forth between this thing, it is a different section, different size of a transmission line. So the overall availability of inductance and capacitance which is going to come can be different. And the reason we saw a difference in frequency when we connected the coupling capacitor is because of this difference in slope. What does it tell you? Which one has so this one we are looking at right now is the lambda by 4 resonator. So the 90-degree one, which has a smaller slope. So smaller slope means smaller characteristic impedance. Sorry, the other way around. We are looking at admittance. So admittance is square root of C over L, right? It's just 1 over that. So smaller slope means smaller capacitance compared to the lambda by 2 resonator, which means a larger inductance. So the L's and the C's have adjusted in such a way that the zero crossing is exactly the same, but the series LC circuit has a smaller capacitance, and hence when you added the same coupling capacitor here, and in your homework and in the last time we discussed that this capacitor just goes in parallel, because the effective capacitance here is smaller, this capacitance has a larger fractional effect on the shift of the resonant frequency, because it now is adding to a smaller number. So overall change is larger for the 90-degree case, which is why the 90-degree resonator ended up at a lower frequency than the 180-degree resonator. Okay, does it make sense now?
It was,
Yes.
so the L's and C's are just different because of the lesser length available in some sense.
Yes, that is part of the reason.
And with it adds differently with the coupling capacitor. And
yeah, well, so adding differential to coupling capacitor is absolutely correct because it is now a smaller capacitor for the lambda by 4 resonator. The coupling capacitor has a bigger effect on the shift in the resonant frequency. So by the way, these are also practically important concepts, is that if you construct two resonators, one lambda by 2 and one lambda by 4, and you put the same coupling capacitor, you will not get you will get two different resonant frequencies, and also the line width might be different, because ultimately we use these coupling capacitors to control the Q factor, right? So that might also be different. So in practice, you have to sort of keep this in mind. Of course, you know, in reality, you design all of this by playing around and empirically tuning these things, but that is the reason. So the only difference between a lambda by 2 resonator at frequency F and a lambda by 4 resonator at frequency F, both having an equivalent equivalent parallel model, is the characteristic impedance of that effective circuit. The transmission line has the same characteristic impedance in both cases. The effective model, which is a parallel LC circuit, has a different characteristic impedance in terms of the effective L and the effective C. But L's and C's are going to match up in such a way that the resonant frequency of just the LC part is going to be identical. But if you have a coupling capacitor, it can push the frequencies differently. Okay, so we can stop there. It's quite long, but you know, these are things which you will get used to more and more as you play around with these things and work more. But I was basically trying to explain some of the subtleties of what is going on. So I will point out the parts of Ozar again, where you should look up these and look at the mathematics of these things carefully. But if there are any quick questions, let me take it now.
We were talking about the when we add a coupling capacitor, then it becomes sort of like an open circuit on the other end as well.
Yes.
I mean, I didn't really digest that properly, I think. Is that irrespective of any capacitance you add, or?
Well, okay, that's a good question. It's because we almost always use this as a small capacitor. Okay. And again, remember, these are sort of somewhat approximations when we talk about open end and short end. It works only perfectly when you have a true open and a true short, which again, in a microwave office model can be done perfectly. But in a realistic scenario, in an experiment, there is nothing called a true short circuit, because this here will be some wire that will have some inductance. So it's not a true short circuit. What does that mean by a true short circuit? Basically, it means that you need omega L to be 0, which means that L has to be 0. But making something with L equal to 0 is, you know, truly L equal to 0 is impossible. So it all depends on what frequency you're operating, and at that frequency, whether that impedance is small or large compared to some other reference impedance you're talking about, in which case 50 ohms. So making an ideal short circuit is easier with a, you know, just by connecting the two pins to each other, but you have to make sure that you do it with a wire or a section which is wide enough and doesn't have like very high inductance. You don't want to make it with a very narrow, thin connection. And similarly, a very small capacitor is easy to make. So, and a small capacitor will have a very large impedance across it, which means that current flowing through this is going to be small. And that is basically what an open is, small current flowing through that. They are not perfect opens or perfect shorts. In fact, that is the reason why having a coupling capacitor changes the resonant frequency, because the boundary condition is not perfectly open or short. We already saw in the last class and in the discussion in part of the homework that this adds an effective capacitance, which basically can also be interpreted as saying that because the adding of the capacitance lowers the resonant frequency and how do we think about a lower resonant frequency? We can think about a slightly longer transmission line. Okay. Now, again, I sort of like these kind of ideas because I had studied a lot of acoustics during my undergraduate days, thinking about open pipes and closed pipes. I don't know. This is not something which is taught that much in undergraduate physics anymore. There also, there is this idea that, you have an open-ended pipe, which means what? Just that there is nothing on the other side. But does it mean that the wave which is traveling in that tube, sound wave, actually just reflects exactly at the point where the tube ends? No, because again, it is related to the impedance the sound waves feel inside the tube and outside the tube. So you always see that the effective length of that tube, which gives rise to the resonance, and these are all very relevant things when you are talking about musical instruments, which are wind instruments. What is their length and how will that correspond to a particular frequency, because that corresponds to a particular note you're trying to play. And you see that the boundary condition not being like a very heavy mismatch means that the effective length looks larger, because the frequency will not correspond to the length of the tube, it will correspond to something which is slightly larger. So it's exactly the same thing happening here, but now in the electrical domain. So the capacitor is not a perfect boundary condition, just like a true open or a true short would be. And that's one way of thinking about why the frequency shifts. Okay. Now I've forgotten exactly where you started. The question is.
It was just the boundary condition imposed by the coupling capacitor. Yeah, makes sense.
Yeah.
It has to be small. So.
Yes, but of course you have complete freedom over this value of the capacitor, and if you keep making the capacitor larger and larger, it now has an impedance which is going to 0, but now this thing is connected in series, then that is just equivalent to not having the capacitor at all. It's like a short here. Then you will not have the same impedance mismatch, because this is 50 ohms and this is 50 ohms. And if you put a very large capacitor, this will cease to be a resonator anymore. That mode will completely disappear. But you can do the opposite. You can put a capacitor to ground and keep increasing its value, because now this is a short circuit to the ground, which is a good impedance mismatch. Okay, we had discussed this last time. In fact, Jay had asked this question about for a series LC, can we put an inductor to ground? Again, a short circuit is easier with a small inductor, but you can also make it with a large capacitor, which in the case of shunting will still form a resonator. So in that case, if you actually start with this situation where you have your port and you have a capacitor to ground, a very small capacitor to ground would actually be a bad impedance mismatch. It basically is like it's not there, because it's not going to pass any current through this capacitance. It's as if not, it's an open circuit connected in parallel. So that is the limiting case where this capacitor, you can consider this, that the capacitor doesn't exist. And in that case, you will not have a resonator, because this is 50 ohms and this is 50 ohms. But as you increase the capacitor value, this will become more and more like a short circuit. And then you reintroduce your boundary condition a lot more precisely. And then whether the frequency comes out to be lower or higher, that all depends on how they are connected and how the inductor is connected. Last time also we saw that the inductor in parallel to the ground pushes the frequency in one way versus the other way. Okay. So I hope this is clear. Jay?
Yeah. It's clear.
Okay. Any other questions? All right. Okay. If not, we'll stop there. I might do another lecture tomorrow. This 6:30 time is okay for all of you tomorrow as well?
Tomorrow I have a class actually.
Sorry, Joydeep?
Tomorrow I have a class actually at 6:30. So after that should be fine.
You have a class at 6:30 to what time?
7:30.
Okay. What about like 4:30 or 5
Yeah, that should be fine.
for others?
Yeah, it's fine.
Yeah.
Yeah.
Okay. I'll
Yeah,
I'll
fine for me also.
I'll confirm tomorrow morning, like before noon. Okay. But yeah, we need to catch up. So we will do that, and then again, we'll at least, as I said, we'll have 2 lectures per week from now on, at the very least. Okay. All right. So see you tomorrow or later.